So as Andre mentioned, homework is due tonight. So sometime before midnight, you should submit it through the Canvas portal. Any other questions regarding the homework that is due? Because we obviously are only a part of the way into chapter 2.
I have a quick question.
Sure.
So I cannot figure out how to change the Word document things. I just put my name on top of the paper because I couldn't figure out how to change my name in the.
So,
Yeah.
Okay, I'm not entirely sure if it makes a super big difference, because if you're loading it through Canvas,
Yeah.
when I push the tab that says grade, I think it slides me along my roster to indicate when I bring up a name.
Yeah.
I think it then displays whether or not a document has been attached. So hopefully, fingers crossed.
Yeah, I put my name at the top of the paper, just
Okay.
in case, but like I couldn't figure out how to change the homework B to. I could not figure it out. So I was like, oh, just
Okay.
put it at the top.
We'll see how it goes.
Okay.
That should be a minor problem.
Okay.
Other questions regarding the homework? All right, we covered a portion of chapter 2, a lot of which was kind of history background-ish stuff, to help give you some clues as to why certain elements don't match their symbols, some clues as to kind of the timeline by which some of these changes and discoveries and laws actually sort of evolved. So we are going to pick up kind of roughly where we left off. This should be right about there. All right, so the last thing we were talking about was kind of basics of the atom. We talked a little bit about sizes. Something else to think about in terms of sort of the nucleus versus the whole atom entirely. Think about your charges. Protons are positive, P and P. Neutrons, no charge, so N and N. Neutrons are neutral. We talked a little bit about the sort of comparison there, about how you have mostly empty space if you're looking at an individual atom. A lot of it is kind of just dead air between where your nucleus is and where the electrons are. I didn't get around to talking a little bit about the size differential, okay? Neutrons and protons are kind of the bowling balls of the subatomic world. They are right around 1,839 times as big as an electron. So kind of think ping pong ball versus bowling ball in terms of their comparison. Something that middle school and to some degree high school texts tend to tell you, which is not actually exactly true, is that protons and neutrons are the same thing, when in fact there is a little bit of difference. Okay, look at the number values that I gave you there. These are actually in grams. I probably should have put a G after it. So proton, the 1.67262 times 10 to the negative 24th grams. And then we have one that is a little bit less. A neutron, 1.6493, also times 10 to the negative 24th. There's actually a reason for this. Okay, so somebody was asking me questions about quarks and stuff last class period. Let me dive into that just a little bit of, in reality, a proton is a neutron and an electron bound together with a neutrino. So there is actually a little bit of a difference there. And actually, I suddenly realized that I flip-flopped my numbers. Well, drat. I will have to send this out as like an announcement. I flip-flopped my P and my N because neutrons should be the 1.67 and the protons should be the 1.64. Yeah, like I said, usually I'm writing this on the board and I catch errors that I do when I'm writing stuff down. I will have to go back and make an amendment to that. It is also in your textbook. Okay. I think I am correct in referencing page 79. Actually, let me grab my textbook and double check that. Yes, it is page 79. Okay. And yes, I did in fact kind of, actually, I know what I did. It was not that I reversed them, it's that I left a digit out. Okay. Because if you actually do happen to look at page 79, it goes 1.67493. So yeah, I do need to go back and correct that. But your textbook is correct. When I typed my notes, I left out a 7 that was supposed to go between the 6 and the 4 there on the neutron end of things. So yeah, that's actually where the error occurs. So oops. Like I said, I usually catch a lot of this stuff when I'm lecturing on the board because I can draw, stuff around. All right, so let's talk about the pieces. We got 3 pieces: protons, neutrons, electrons. We've got like 116, 118 different elements. Well, how do you get all those different elements if we only have 3 pieces? It's all about the numbers. How many of those pieces do you have? And most critically, the number of protons is actually what allows you to identify your element. So let's pick on hydrogen. Hydrogen being the tiniest. So hydrogen doesn't even have any neutrons. It's in its normal state. Hydrogen has 1 proton and 1 electron. That way we have 1 positive and 1 negative, and everything cancels out, and no neutrons at all. So when you're actually looking at the periodic table, if you look at one of the boxes, in addition to the symbol, 1 or 2 letters, you also see a number written above it. You see a number written below it. Usually one of those is a whole number, and most of the time one of those is a decimal number. So if you look at iron, okay, and iron is number 26 on the periodic table. So also in the same box with the number 26 and the Fe for iron, and if I round it slightly depending upon which textbook you're looking in, you'll also see 55.847. So this kind of brings up some questions. So one of the things that I wrote there about the atomic mass is protons plus neutrons. Then that kind of makes you think, well, okay, iron has 26 protons. If we did mass minus protons, that should give us neutrons. The math seems to work, except it looks like we have weird fractions of a neutron. So do you really have 0.847 of a neutron? No, actually not. So what the decimal number does for you is it utilizes a mathematical calculation that I will call a weighted average. Weighted averages are also based upon isotopes. Most elements have at least 2 isotopes. Some have like a dozen or more. It really kind of depends upon the element. Even lonely little hydrogen actually has more than 1 isotope. There's the normal average everyday isotope of hydrogen, which has 1 proton and 1 electron. There's a slightly heavier but not radioactive one known as deuterium that has 1 of each, 1 proton, 1 neutron, and 1 electron. And then there's a very bizarre radioactive version of hydrogen that has 2 neutrons, 1 proton, and 1 electron. So if you look at the number, the digital number, the decimal number under hydrogen, most textbooks will list it as 1.008. So not exactly 1, because there are these other 2 isotopes. Now, part of this is tied into the fact that there are different numbers of neutrons, which is also tied into AMUs. Okay, AMUs is an abbreviation. 1 letter for each word, atomic mass unit. So if you have a carbon-12 atom, okay, note when I look at my C there, the 12 that's written beside it is kind of upscripted a little bit and a little bit to the left. And so this is a common way of writing an element in such a way that you can actually tell which isotope it is you have. I can't easily get Word to show the bottom number at the same time as I show the top number. So like carbon is number 6 on the periodic table. And if you look at it in your textbook, you will see the 12 over top of the 6. So I'm gonna stop my share for a minute, and we're gonna try to do really old school whiteboard. Okay, literally whiteboard. And it should look like this, okay? It should have the 12 up above, and it should have the 6 down below, and they are both on the same side of the element symbol. So this is really, truly traditional isotopic notation. So, like I said, I haven't got an easy way to get my Microsoft Word to display a number on top and a number on the bottom where they're actually like vertically above each other. So that kind of puts me in a little bit of a quandary there. So let's go back to talking about the isotopes themselves. So I decided to pick on one of the smaller elements, magnesium. Magnesium has 3 different versions, 3 different isotopes. We've got the popular, aka common one, which comes with a percent abundance of 78.7%. So think about it this way. If I went out and dug up a sample of magnesium that has like magnesium ore or something like that, and I picked out 100 samples, 78.7 of them would be that version of magnesium. But there are 2 other versions. They're just a whole lot less abundant, a whole lot less popular. We've got a version that is known as magnesium 25, and there's also another one that is magnesium 26. Now, all of these have different numbers of neutrons. Every single one of them has the same number of protons. In order to make the math work, you take the weight of the isotope. So in this case, we've got a 24, a 25, and a 26. And we are going to move the decimal place because a percent sign is a decimal after it's been multiplied by 100. So we're going to kind of undo that. So if you multiplied 24 times 0.787, you will get 18.88. Next line. If you multiply the 25 times 0.1018, you'll get 2.53. And the last one, if we multiply 26, again, we're moving our decimal place, 0.1117, you get 2.90. Now, one of the biggest differences between a weighted average and a regular average is there's no division step. A standard regular mathematical average, also known as a mean, M-E-A-N, would add them all up together and divide by 3. Well, part of the reason you're not allowed to do that is they're not all equally common. We've got one that's really common, and then we've got 2 that, yes, they exist, but there's a whole lot less of them. So when you do your weighted average, first you have to do the multiply step, then you total them. So in this case, I get 24.31 as my weighted average. So depending upon if you're looking at your textbook or there's obviously a large number of other variations on the periodic table that are available on the internet, you might see 24.305 listed as the atomic mass. I rounded it to 2 decimal places to give me the 24.31. So no division step. This is actually even how everybody does grades. Okay, so for instance, when you look at your syllabus and it says 45% of your grade is due to tests. So I take your test average, that's a regular average, but then I multiply it by 0.45. Your homework is 13%. So homework average times 0.13. And so I kind of do the whole deal, except for the fact that I'm multiplying times a percentage each time, and then going ahead and totaling them up. And like I said, this is how grades work too. All right, let's look a little bit more at the whole concept of protons, neutrons, and electrons. If I tell you which isotope of a particular element, you should be able to figure out how many of each of these 3 regular subatomic particles there are. So carbon-14, yeah, that's the radioactive one. Carbon is number 6 on the periodic table. Again, we're running into that problem of me not being able to show you that the 6 is kind of on the bottom there. So in a regular neutral element, protons have to equal neutrons. All your pluses have to cancel out all your minuses. Later that will change. But for right now, we want them to match. So for my carbon-14, I've got 6 protons and 6 electrons. Now it's tempting to look at the 14 and go, oh, there's 14 neutrons. No, you actually have to subtract. The number, the upscripted number, is never going to be the answer to any of those pieces: protons, neutrons, electrons. I got to subtract. So 14 minus 6, that'll give me 8. So how about one that's a little bit bigger? I picked on gallium. So gallium is a semi-metal. It has uses in batteries and some other things like that. It's number 31 on the periodic table. So 31 protons, 31 electrons, 39 neutrons because I subtracted. So 70 minus 31. That'll give me 39. Simple subtraction. So some more kind of, in some ways, this is a little bit backgroundy, although it will come back again at a later point. Why are we using AMUs and why are they stuck on carbon? Carbon is relevant from a we're alive point of view. Carbon is one of the most common organic elements. We pick on the one that is the most common because carbon has three versions. We've got carbon 12, which is about 98%. We've got carbon 13, which is kind of not quite 1.5%. Carbon 13 is also not radioactive. And then we've got a few very small tenths of a percent of carbon 14, the radioactive version one. So I don't know why, I don't know why exactly, but this is what was decided, was that they were going to use carbon as the basis for this. So if we assume that a single carbon 12 atom weighs the number there, 1.99 times 10 to the negative 23rd grams, and we assume that we are going to then divide by 12 because there are 12 nuclear particles, protons plus neutrons. And you get the gram mass of a single AMU, 1.66 times 10 to the negative 24th. So it'll come back again a little bit in the following chapter. We'll kind of revisit AMUs a little bit when we get to chapter 3. So you see it a bit here. It doesn't have a lot of use in this particular chapter, but it will come back around again. All right, some more kind of background on our way to other things. We already talked about the whole atom is the smallest element of, I said that wrong. Atom is the smallest piece of an element. Molecule is the smallest piece of a compound. We briefly touched on chemical formulas. There's a little bit of an introduction here in the middle of chapter 2 that kind of revisits that. Keeping in mind that when you write out your chemical formulas, they don't write their ones. So look at that first molecule there. We have MgSO4. So since there's no number written to the left and down, actually to the right and down, of your magnesium, you have one magnesium, you have one atom of sulfur, but there is a number beside the oxygen. You have 4 O's. What if there's parentheses? This is a lot like algebra. This is part of the reason why algebra also is a prereq for the class. So look at my NH4. It's got parentheses around the NH4 part. There's a little 3 on the outside, and then I have a PO4. So I actually have 3 atoms of nitrogen, because the 3 on the outside multiplies the 1 times the 1 on the 1 N on the inside. Multiply your 4 and your 3 together, I have 12 hydrogens, 1 phosphorus, and 4 oxygens. The number on the outside of parentheses only operates sort of back to the left. It does not go forward. It only affects the things that are inside the parentheses, and it doesn't affect the phosphorus, and it doesn't affect the oxygen there.
But it's still one molecule, right?
Yeah, it's still a molecular formula.
Just one molecule.
Yes, one. So something else that we'll run across, and we only see a little bit of it in this chapter. This again is one of those things that gets touched on here and comes back again in a later chapter, is how would the molecule actually look if you built it with Tinker Toys? We have molecular Tinker Toys. I'll probably actually, on one of the last labs of the semester, show them to you so you actually have an idea how they look in reality. I'm actually probably going to scav some from work and bring them home so I can show you on Zoom kind of how they look. But let me talk about the structural formula thing. So let me stop my share again. All right. One of the molecules that is most likely to undergo this whole idea is acetic acid. So this is acetic acid written in, we'll call it the standard inorganic way. So let me write it again. There is another way that you can write it out that gives you just a little bit more information. So for this one, you can see the CH3, I'm trying to hold it so it doesn't like reflect too badly. The CH3, then there's the second carbon, because there are two carbons in this molecule, and the two O's are drawn side by side, and the final hydrogen kind of dangling off to one end. So one is kind of the ultimate shorthand version. One is a more organic version to write it, as in like, as if you were taking organic chemistry. And then let me do the last version. The last version is way more indicative of how the molecule is built. All right, so we see a carbon that has three little spokes coming off of it, and they are each a hydrogen atom. Then you have your second carbon with a double bonded O poking upward. Then you have another O, actually linked to that second carbon too, and your final hydrogen is kind of dangling out there on the end past the second oxygen. So that is a structural formula. So you see a little bit of them in this chapter, but not a lot. They are somewhat helpful in kind of getting a grip on how some of these atoms actually kind of fit together to make a molecule. So I don't have an easy way to put all of those things sort of back into my document. I'm working on document illustrations. I amended some other stuff. I may repost the notes, an updated version in the next week or two. So you might want to check back and see if there's been an update. So we're going to go back to the periodic table again. It's called periodic for a reason. So going across from left to right, there are 7 horizontal rows. These are also known as the periods. So if you look at things that are in the same period, we will later discover that that tells you certain things about how their electrons are arranged. But sometimes we pay more attention to the columns. Columns in some versions of the periodic table are numbered 1 through 18. In a, I will call it my more preferred version, they are labeled with Roman numerals. And so the Roman numerals are actually a way of kind of grouping them that gives you a little bit more information. They have Roman numerals and then A's or B's. So if you start at the far left-hand side, this is a group. It has hydrogen at the top, of which we're gonna, for a moment, ignore. We're actually gonna jump down to the next element on the periodic table, which is lithium. And if you look down the periodic table, you will see lithium, sodium, rubidium, cesium, and francium going downward. Now this group, sometimes referred to as group 1, is known as alkali metals. So some of these groups have, we'll call them names for the family. And alkali metals have certain things in common. If you actually looked up the melting points, you will find that most of them melt anywhere from barely above room temperature, things like cesium and francium, to kind of lukewarm, at least lukewarm on the Celsius scale. Lithium melts somewhere around 50, I believe. Don't quote me on that. I actually don't have that number right at my fingertips. But lukewarmish. They also, you will find pretty much all textbooks claim they are soft. So let me tell you a little tale. We bought some sodium as a department for the purpose of doing some demos. And it comes in what kind of looks like a paint can, because as you see, the final line of this group is they react with water, but they also react with oxygen in the air. So when you get them from the manufacturer, they're in this little thing that looks like a paint can, and it's filled with mineral oil or kerosene to prevent it from reacting with the humidity in the air or the oxygen in the air. So because, we're always led to believe that, they're kind of like relatively soft, we took one of the metal spatulas. For those people who had lab this week, they got to see the spatulas when they were weighing them in the Experiment 1 lab. They're just kind of like a piece of metal that's bended, or bent rather. So we grabbed up a metal spatula and went, okay, well, I'll just like kind of chunk it in parts, kind of like butter. Yeah, that didn't work. Soft is apparently a relative term. We ended up having to borrow a bone saw from Anatomy and Physiology to actually cut the sodium into chunks, which we can then store in smaller containers with kerosene. So that was kind of an interesting reality check in some ways. Soft is a relative term. Soft means, okay, I don't need a jackhammer, but I need something more with more oomph to it than a spatula. Somewhere on YouTube, and maybe I should actually look up this particular video. Somewhere on YouTube, if you put in the search terms of like sodium, fraternity, and explosion, you will find a video of a couple of frat boys who, how they got hold of a chunk of sodium that's about as big as their fist, I don't know. But they have this giant galvanized steel tub out on the front lawn of their frat house, and they filled it with water, and they heaved the piece of sodium into it, and it goes kablooey. So it was fairly impressive, and I'm kind of surprised they didn't get a Darwin Award out of it. So yeah, it's out there somewhere. I think it's still on YouTube. Hopefully you will not attempt to repeat that. So let's skip down to the next group. We've got the next column over. This one, we're not going to ignore the element that's at the top. So beryllium, magnesium, calcium, strontium, barium, and radium. Now, these have a similar name, but not the same. They are known as alkaline earth metals. So if you allow them to react with oxygen, you would find out that their oxides in the world of pH are really basic. Some of these actually burn pretty well. Magnesium in particular, if you go to like Dick's Sporting Goods or something like that, sometimes you can buy this little vial of shavings, and they call them campfire starters. And you set the magnesium on fire and it burns unbelievably white hot, okay, but it'll light even wet wood. Magnesium burns underwater. If you have ever watched any videos of underwater welding, they are often using magnesium torches to do underwater welding. So here's more trivia. F-18s and other currently in operation fighter planes that are on the carriers, their shell basically is made of a metal that is not quite pure magnesium, but it's pretty close. And I have been told that aircraft carriers become equipped with a special bulldozer, because if your F-18 catches fire, you can't put it out because you can't put out a magnesium fire with water, and they just push them overboard so that they don't burn down through the deck. More interesting, fascinating.
I can speak to that. They call that a Class D fire, and yeah, they push them overboard.
Yeah, because you can't put them out.
No, it's impossible. Burning metal. That's basically what happened in San Diego. I mean, once metal actually starts to act as a fuel, forget.
Yeah, that was like what, 2 weeks ago, 3 weeks ago.
Yeah, they often use a halon system to.
And I heard it was offline. Since my husband works for the shipyard, he and his buds were all talking about the fact that it caught fire, and that because it was in for work, I think, for repairs.
Yep.
So
yep, it was.
Yeah, bad situation.
But most of the hull of a carrier is going to be either HY, which is a high yield carbon steel, or low yield.
So, but if you get something hot enough, it'll still melt.
Oh yeah.
All right, we are going to skip to the opposite side of the periodic table. We're going to skip to, and this is known as group 7, usually Roman numeral 7. Fluorine is at top. Chlorine, bromine, iodine, and yes, there is one more element underneath there that is labeled AT for astatine. It is both radioactive and has very few uses. So know that it exists. You're kind of unlikely to see it in the molecules that we will be talking about as this chapter continues. So these are the halogens. Okay. Halogens as in the same stuff they put in your headlights, okay? Usually halogen headlights, some of them are just fluorine, some of them are a mixture of fluorine and chlorine. All of them are relatively reactive, highly reactive in and of themselves. Basically, you can't go out, say, and dig up as an ore pure fluorine, chlorine, bromine, or iodine. Usually it is attached to something else. Sodium chloride, table salt is one of those possible, kind of common options there. Silver bromide is found in small amounts in seawater, also used in photography. Potassium iodide. When you buy a box of salt, okay, and it says iodized salt, okay, sometimes it's sodium iodide, but sometimes it also contains potassium iodide, especially for people who are trying to avoid sodium. So you're going to see the halogens a lot. They are super common, but they're almost always hooked to other elements. Then we get to the last, most right-hand column, often referred to as group 8. These are known as the noble gases. So we've got actually helium's at the top, and you kind of step your ways down, and then you've got kind of krypton and xenon toward the bottom. One of the things that's true of those, and you wouldn't necessarily immediately think about this, is unlike halogens, their buddies next door, they are super non-reactive. This is one of the reasons why we no longer use hydrogen in dirigibles. We now use helium, because if you have hydrogen in your dirigible, you have Hindenburg problems, as in kablooey. Helium doesn't burn. This is also one of the reasons why neon lights, even though they get very hot, they generally do not burn unless they get contaminated. If you have been to Vegas and seen the Luxor, it has a unbelievably powerful light right at the tippy top of the pyramid, so that the planes flying out of McLaren don't hit the pyramid on the way out. But because it needs to burn very hot for many hours at a time, it has xenon in that searchlight, because xenon is incredibly non-reactive. Now, I'm gonna grab my lab book and see if I can show you the staircase that comes up next.
We use argon and TIG welding a lot because it's a good shielding gas.
Yeah, that would actually make sense. Okay, my lab book doesn't have what I'm looking for. Hang on a minute. Let me see if I can find a good example here, picture-wise. Of course, it's not going to give me what I want. Okay, this is page 95 in your textbook. And it's not super, super obvious, but if you look at the colors, oops, my book falls shut there. If you look at the colors, all the ones down here and all the way across, they're yellow. You get this kind of stair-step effect that starts there where the aluminum is, and actually technically it starts kind of, the staircase starts kind of between the aluminum and what's below it. And then it kind of takes it one block at a time, and you can kind of see where the color differential is there on a diagonal going down. Okay, so this is what I actually am implying by talking about the staircase there in the notes. So the staircase is a separating point. What the staircase does for you is it helps you differentiate between the metals and the non-metals. So all of those things that are yellow, which is like 3/4 of the periodic table, are metals. There are way more metals than there are non-metals, which doesn't sound intuitively obvious. It sounds like kind of a what moment. Now remember that in terms of, you know, where you find them on Earth and things like that, remember a lot of these are sort of locked inside of rocks. Okay, yes, there's metals there, but like you can't usually dig most metals in a pure state from the ground. Gold, silver, copper, that's a little different, but a lot of those metals are part of a molecule and you have to refine them. Now, the big segment that is sort of squashed down in the middle of the table there, they have an even slightly more specific set of names. They are known as the transition metals. They run from scandium, SC. They're at the left-hand side of the swashdown part, all the way over to zinc, because we're going along the top line there. And they sort of kind of run a little bit down that diagonal. If you actually look at the bottom two rows, so one of them, if you actually have your page 95 available, it has a little box there, which then has an arrow, and it points toward the bottom of the table. So that segment at the bottom, which looks like two stripes, one of them, the top stripe, is known as the lanthanides, partly because that's the first element of that set. And then the bottom element there, the bottom stripe there, starts with AC for actinium and runs all the way over to LR, which is lawrencium. So what we're doing is we're taking the periodic table and we're kind of breaking it into chunks. And what those chunks do for us is help us eventually in categorizing some of these things for the purpose of naming. So it's a more of a stepping stone thing as we're going through this chapter. So metals themselves have some things in common. Now be aware, not all of them do it equally well. Metals conduct heat and electricity. Now, if you're running wires in your house, copper is a good bet, okay, conducting heat and electricity, okay. Technically speaking, you could use something like sodium, but that would be a really big problem. So yes, they do conduct heat and electricity, but some of them are way more useful or better at it than others. Some houses built in the 70s went through a phase where they used a certain amount of aluminum wiring. There's some heat and oxidation problems involved with that. So malleable, okay, buzzword here. Malleable means, more or less, can be pounded out into a flat sheet. Now, again, certain things do this better than others. We were talking about the gold foil that Rutherford was using in his experiment last week, or back on Tuesday. You can pound gold out until it's almost see-through. Other things, not so much. Ductile is kind of an offshoot of that. Ductile means can be drawn into a wire. And again, we get this problem of, yeah, certain things do this really well, other things not so much, but they all have the capacity in one version or another. And lustrous. Think back to the physical characteristics that we were talking about in chapter 1. And one of the things I mentioned there was luster or shininess can give you clues about its purity. So if you have a sample that is sort of dull and unshiny, it could be because it's coated with a layer that has already reacted with the oxygen in the atmosphere. Shiny things in terms of metals tend to be more pure. Now, up in that right-hand corner, the ones that are not yellow, okay, on that periodic table, and there's not very many of them. We've got kind of from boron over in the direction of the noble gases, and then we could go kind of down that diagonal. They don't have as much in common. We can make some generalizations out of them. We can look at them and go, well, some are liquids, bromine specifically. A lot of them are gases. Now, there's a whole bunch of them that are gases there. If you kind of look across your table there, you could go, well, okay, nitrogen, oxygen, fluorine, There's all those noble gases down the right-hand column there. Chlorine's a gas. Sulfur, no, not usually. Bromine's a liquid. Selenium is actually a solid. So that's why I put the word many in there, because it's not a particular uniform collection there. Now, there are three particular elements that are there along the line. Some textbooks, and actually I forgot to double check about this, the opinion of this particular textbook. Some of them will lump boron in with this group. Some of them will lump antimony in with this trio. But all the textbooks will agree that silicon, germanium, and arsenic all get categorized as semi-metals, also known as metalloids. Now, looking at that particular trio, maybe here in our modern day society, as we're all sitting here Zooming, it should make you think, ooh, computer stuff is made of those. So one of the deals is they have some of the characteristics of the metals. They're really good at the whole conducting electricity idea. They're also lustrous. They're not so malleable and ductile. But you can use those three elements and sort of embrace the idea that they're not really metals and they're not really non-metals. And that gives us capabilities that we didn't used to be aware of. You know, we're talking, what, 80 years ago? And I kind of revisited the whole biological thing again, since we're talking about clusters of elements on the periodic table. So back to CHOMPs: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. So the last little bit that I want to get into tonight begins the saga of nomenclature. And we're going to start with sticking two of the same molecule together. That is the simplest possible way you can get from an element to a molecule. So if you stick two of the same one together, there's a batch of gases that occur this way, but specifically there are 7 elements. Okay, brain tricks, mnemonic devices. There are some other ones. This is the one I'm most familiar with. Old Brown Finch. So those 7 elements all occur naturally in the diatomic form, especially oxygen. Oxygen is hardly ever found as a single atom. It always wants a buddy. So do pretty much all of the other things there. So we've got the O in the old stands for the oxygen. The Br in the brown gives you bromine. And I know it's a little bit of a brain hiccup there. The C in Finch is not carbon. The C in Finch is actually chlorine. So fluorine, iodine, nitrogen, chlorine, and hydrogen. But it's a good way to keep track of the ones that like to be diatomic. So back in the beginning part of the chapter, we talked about wanting an equal number of protons and electrons. Now we're going to begin to stray away from that idea. In fact, a lot of the time, you will not have an equivalent number of protons and electrons. So you get an ion. Ion means it has a charge. 2 possible charges, cations and anions. I know it looks like it's spelled cation, as in like we all want to go on vacation. Please don't pronounce it cation. They are known as cations. It's pronounced as if it were 2 separate words. So lithium and calcium like to make cations. More brain tricks here. Cation has a T in it. A T looks like a plus sign. Therefore, it is a way to remember that cations are the positive ones. You can't add positives. You can't add protons to your atom. But you can take things away. Specifically, you can take away the electrons. If I look at lithium, lithium's number 3 on the periodic table. So that means it has 3 protons. And in the beginning of its life, it has 3 electrons. But lithium, being an alkali metal, has a tendency to lose an electron, usually just one. So now I get to the case where I have a lithium cation. Now the reason it's a cation is I've still got the 3 pluses, but I only have 2 minuses. Think of it kind of like unveiling or revealing the plus that was always there that's now no longer masked by a 3rd electron. You've peeled that 3rd electron away and it went to live with somebody else. And now you see that 3rd positive charge. Let's pick on calcium. So calcium's an alkaline earth metal. Alkaline earth metals have a tendency to make +2 cations. Now calcium's a little bit bigger. Calcium has 20 protons. But if I steal those 2 electrons away, pull them away from my atom, send them somewhere else, and I still have 18 left on the electron end of things, but I've still got 20 protons because that's actually what makes it calcium. My 2 little positives that used to be covered up now are unveiled. So I have a +2 cation created by my calcium ion. Let's now go to the opposite end of the situation. Since we can peel away electrons, we can send them to live with somebody else. Often, they will go to live with non-metals. Anions are the negative ones. They stole or gained 1 or more electrons from somebody else, probably. Fluorine. Fluorine starts out life with 9 protons and 9 electrons. But fluorine is an electron pig, okay? It likes to go steal electrons from everybody else. But it only steals 1. So now I've got a situation where I have 10 electrons and only 9 protons. And I have an F with a negative charge attached to it. So it is now a fluorine ion, or more appropriately called a fluoride. Oxygen likes to steal 2. It starts out life with 8. If it goes and steals 2 from somebody else, maybe it's stolen from the calcium. Now I've got 10 electrons. So my oxygen has a -2 charge. Now, one of the things that you will find is inconsistent between various textbooks and various websites and etc. is some textbooks will write the number and then the charge, like 2 positive, 2 negative. I learned it the other way, and part of me thinks from a number line point of view, it makes more sense to write +2 or -2 or -3. It's not wrong the other way. It's just a different variation, but so that you are aware, you may run across this as sort of like a difference between different sources when you are looking at ions, for examples. Some of them will have the sign out in front, and some of them will have the sign at the end. So now we are beginning to embrace the naming rules. Now, things that are cations are not conjugated. Remember I said it's kind of like learning a new language? We don't conjugate the cations, kind of like we don't conjugate nouns in English. If it's an Na with a plus, we just call it a sodium ion or sodium cation. The calcium would just be a calcium ion or a calcium cation. The anions, though, they get conjugated. They end up with a different suffix. So once I have attached an extra electron to my fluorine atom, it is no longer just fluorine, it is fluoride, as in that stuff that's in your toothpaste, okay? Oxygen becomes oxide. Now note, I lost a whole lot more of my root word here. You can look these up. There's a whole table full of them to look at in your lab, both your lab book and your textbook. A lot of the non-metals only keep maybe 2 to 4 letters of their root name before they attach the IDE ending. So I gave you a typical one there that is a tempting thing to do, to call it oxygide, but no, they actually get rid of way more of the letters there and it just becomes oxide. So one last thing then, look at the pattern here, okay? We're ignoring all the transition elements at the moment. They're a whole separate issue. If you go from left to right across the periodic table and you skip the big gap where all the transition metals are, there's a pattern. All the alkali metals like to be +1s. All the alkaline earth metals like to be +2s. Boron, aluminum, and sometimes gallium and arsenic like to be +3. Carbon, silicon, and sometimes the stuff below that like to be 4s, but sometimes it's +4 and sometimes it's -4. It really has to do with who they are sharing their electrons with. Nitrogen, phosphorus, and sometimes the stuff below that like to be -3s. Oxygen, sulfur, and selenium like to be -2s. Halogens like to be -1s. And then we get back over to the noble gases who hate everybody. And they almost never have a charge, and because it's just always pretty much 0. So that's kind of where we're going to end tonight. This gets us about 60% of the way through chapter 2. We have yet to finish the chapter. My recommendation over the long weekend is take a good stab at doing the front page of your chapter 2 homework. We have not gotten to all of the deep, dark nomenclature rules yet. You can take a stab at them, but that's what we're going to be focusing on Tuesday, is digging down deep into all of the nomenclature rules. So don't get behind. Try to take a stab at them, at least the front page of your homework over the weekend. I think 9 or 10 people have already turned in homework for chapter 1. If you have not done so, try to make sure you get it submitted before midnight tonight. Things I'm going to be doing of my holiday weekend involve grading papers. I will post the answer key probably tomorrow to chapter 1, so at least you can look through it and decide if you got them right or wrong. And then I will actually go through the homework set answers on Tuesday, prior to working some more on chapter 2. So we are clunking along. We are heading in the direction of the first test, but it's probably going to be about a week and a half to 2 weeks, roughly, before that first test occurs. Questions regarding homework that's due tonight or upcoming homework? Hopefully we're all beginning to get a little bit of a handle on this. We're all trying. And I posted Tuesday's link, YouTube link, for anybody who was not around for the actual Zoom on Tuesday. I did finally get it crank through the YouTube system, and it's posted, and then I put the link at the top of the lecture Canvas shell. So if you want to go back and watch a part of it or something like that, because remember I did an example on the whiteboard there that's actually not in your notes, if you want to go back and have another look at that. Questions?
I got one question, but I got to deal with the lab.
Okay, that's fine.
It just one on the I think it is experiment 1 pre-lab assignment.
Okay.
7 and 8. It was talking about doing experimental procedure parts C1. Was that part of our lab on Monday?
Yes.
Or-
Yes. C1. Let me look it up.
Because I might have missed that when I was doing that in lab. I might have skipped that because I was going through. Oh, okay, I got you.
So A was Bunsen burner, and
B was the balance lab.
B is balance stuff,
Mhm.
and then C is density. So C1 specifically applies to doing the density of the big solid cylindrical chunk.
I got it. Okay. All right. I got you.
That's what it's asking you about.
Okay. All right. That's it now. I was going crazy.
Yeah, they're labeled kind of weirdly. It's like the letters are along the far right-hand edge of that page. I don't know why it's done that way, but it is.
Okay. That worked.
Other questions? Also, since some people have not had lab with me yet, the group B people, if you are having trouble getting your lab book, if it's coming slower because you mail ordered it or whatever, I posted a digital copy, PDF copy of Dry Lab 1 because Mr. Wheaton also found out that a whole bunch of his students were having trouble getting the lab books fast enough. So Dry Lab 1, the digital version of it, is actually loaded to the lab shell for Canvas. If you haven't, if you're like haven't got your textbook yet, but it's coming. So hopefully that will help some people out who kind of are like in this limbo of, well, I'm supposed to be doing it, but I don't actually have the lab book yet. So it was scanned and posted as a digital version.
Gotcha.
The people who don't have me for lab probably can't view that digital version. Hopefully, though, both Dr. McHugh and Mr. Wheaton also, because Mr. Wheaton is he's one level up the food chain from me. So he sent it out to all of us who teach 111. So I am assuming that all the people who have a 111 lab have access to that and are hopefully posting it to their Canvas shells. Other questions? Hopefully that will be helpful. All right. I guess have a nice holiday weekend and don't get the virus and all those fun things. And we're all probably mostly going to be hanging out in our own backyards.
Also, yeah, like I said in text, sorry it was late.
If the what?
Like I said in the text chat, sorry I'm late. I was
Oh, that's
late.
fine. Like I said, after this gets crunched by the Zoom system, I will post the link to this lecture probably not until tomorrow night or Saturday, because it takes Zoom like 9 hours or something to crunch it into a file, because we're all doing this. And it's kind of overwhelms the system a little bit. But then once it gets crunched, then I can translate it to YouTube, but even YouTube takes a couple of hours. So the earliest I might post this lecture for, if you need to view parts of it, is probably going to be tomorrow night, but Saturday morning sometime is more likely. Like I said, I know that not everybody has easy access to the live streaming part, so I'm trying to keep up, trying to make sure that I post all the lectures to the Zoom link thing there on Canvas, so that you can go back and listen to one part if you need to, or if you miss something, you can go back and listen to that. Other questions? So if you did not submit me homework already, please try to make sure you get it in by midnight tonight. Obviously, I'm probably not going to be up that late, but the system will be. I'm not grading them till tomorrow. See you guys next week.
Good one.
Thank you.